All right, hello out there in internet land. It's time to review your AP Physics C mechanics. And we're going to start with some basic review of motion graphs and representations and all that delicious stuff. Now, tell your Physics 1 friends, because this one turns out has a big overlap with AP Physics 1, so they can watch it on the replay if they want. But this one has a pretty big overlap there with Physics 1 and that kind of thing. We're going to do the more calculus-based stuff next time, so stay tuned for that. So we're going to do 2 days, today and tomorrow, of just one-dimensional motion review. It's not my favorite physics topic. I'm going to be completely honest with you. I like to talk more about forces and energy, but kinematics, motion is pretty foundational to everything that we do. We really can't talk about forces, energy, and momentum, rotation, and all that really interesting stuff without having some kind of understanding of how we're communicating motion. So that's why we do kinematics first most of the time, right? Okay, my name is John Frensley. You know where I am, Prosper High School, and this is Physics C Mechanics with a pretty heavy overlap for Physics 1 this time around. Okay, so I'm going to give you all a warm-up, all right? So here's how the warm-up's going to work. I want you to look at this verbal description. I want you to consider a car. It starts from rest. It's a red light. Light turns green. At time equals 0, the light turns green, so the car is going to speed up for 5 seconds. Then it's going to go a constant speed for 5 seconds. Then it's going to come to rest again over 5 seconds as the car approaches a stop sign. So you're going to want your pencil and paper ready for today, or a whiteboard or something like that that you can write with, and just get ready, because you're going to draw a position versus time graph, give it a 5, 10, 15 on the time axis, velocity versus time, give it a 5, 10, 15 on the time axis, acceleration versus time, one more time, a 5, 10, 15 on the time axis, and so you're going to draw, you're going to sketch. What does sketch mean? Sketch means you're really just trying to get the shape, okay? So on the AP Physics exams, when they say sketch, it's like, really, we just want to get the shape. Draw means we really want you to get the shape, but also line it up with the numbers correctly, okay? So there might be numbers on the axes. And then plot means you're making dots from data, like lab data, and you're going to draw a best fit line or curve. So this is really a sketch. And I would like for you to pretend for me that the speeding up and the slowing down are constant acceleration, speeding up and slowing down. Okay, so speed up for 5 seconds, constant speed 5 seconds, slow down to rest for 5 seconds. And let me give you some music. On your mark, get set, go. right, as the timer ticks down. A programming note. If the music bothers you, then feel free to just mute it while the timer's on. You're not going to hear anything interesting from me while the timer's on, and then just unmute it when the timer's off. So, to each his own, right? You have a mute button on your computer, so there you go. I also have a mute button. It just doesn't work anymore. Okay, so you're going to see what the answer to that little warm-up is, but we're going to see it a little bit later on, probably about 5 minutes. Let's have a look at kind of what we want to talk about today. So really what we want to do is we want to take a qualitative, that means we're just looking at the shape, position, velocity, acceleration versus time graph. We want to sketch the other two. All right. So if I give you acceleration versus time graph and I'd really just show you the shape, I'm like, hey, what's the shape of the velocity graph look like? That's kind of what we're looking at, right? Now, what if I give you a quantitative velocity or acceleration versus time graph? Can you draw the other one and the position graph? So quantitative means now there's going to be numbers, right? So there's going to be numbers horizontally and vertically. Then can you draw the other two graphs with scales with numbers? That's what quantitative means, right? Okay, and then actually, this is wrong. This next one is going to be on our next discussion, so somehow it snuck into this PowerPoint, but what we're going to do is we're going to deal next time with what's called segmented motion. So what happens if I say, okay, so the car has an acceleration of 5 meters per second squared, and then the car has an acceleration of 2 meters per second squared, how far does it go? And it's like you have to treat it as two separate problems. So sorry about that. That last bullet point is not today. That's actually tomorrow. I thought I'd fit it in today, but you know what? We only got 45 minutes, and I'm going to try to make the most of it I can, right? So here's what you need to know, and this is going to be super boring. I really hope that this is not new information to you. Here it comes. The slope of a position versus time graph is velocity. Okay, I hope you know that already. All right, that's the only rule you need to know for position versus time graph. For velocity versus time graph, you need to know two rules. So here they come. Let's just say them together. The area of a velocity versus time graph is change in position, which is also known as displacement, right? So if you take the area of a velocity versus time graph and the area is 10, that doesn't mean that the object is at a place called 10. It means that it advanced ahead 10 or something like that. You know what I mean? Okay, let's say the other one for velocity, it starts with the slope. The slope of a velocity versus time graph is acceleration. I really hope this isn't headline news to you, okay? So last one for an acceleration graph. This is one that is probably the least practiced of all the rules, that the area of an acceleration versus time graph is how much velocity changes. But I think especially in AP Physics C, that's going to be a big deal. Maybe in Physics 1, I don't know. I don't know. It's less likely to show up on a P1 exam, but that last one might show up on a Physics C exam. So please make sure you know how to change position to velocity to acceleration using slope or area. Okay, so here's the go to it. Here's the go and stop. So I already drew the position graph. So what was the story? The story was that we started from rest. And so my position graph starts with zero slope. All right, so I start with zero slope, zero velocity. I start from rest. Okay, everybody see my little magic arrow right there? All good. So now we're going to speed up. So the slope of a position graph's velocity. So if I'm gaining positive velocity, that means that the graph must be becoming more and more and more steep. So as the graph becomes more and more positive slope, more and more steep, then that tells me that the object is speeding up. But if the object has a constant forward speed, then that's going to be a straight line segment. So straight line on a position graph is a constant velocity. And then to slow down, I need to have my slope approach zero. So I go from a positive slope to a zero slope. And if you're trying to draw these, it would be best to not have any kinky, parts that you could poke your eye out on, but just make it smooth. So I worked really hard to make that parabola transition smoothly into the line, transition smoothly into the parabola. So how am I going to make the velocity versus time graph? Well, let's take it one segment at a time. So here's my segment of position where the position starts with zero slope, no slope, zero slope, and gradually becomes more and more positive slope. As the position graph goes from zero to positive slope, the velocity graph is going to go from zero to positive velocity. So velocity starts at zero height on the velocity graph, and now it's positive height on a velocity graph. For those of you who are in Physics C and know calculus, you know that the derivative of a parabola is a line. For those of you who are in AP Physics 1, you know that a constant acceleration is a parabola on a position graph, and a constant acceleration is a straight line on a velocity graph. Now, we have a constant slope here. We have a constant slope here in the middle segment. So constant slope, constant velocity, constant slope on position graph, constant height, constant velocity on a velocity graph. And then as the slope decreases back to zero, from positive slope to zero slope, the velocity decreases from positive velocity back to zero velocity. So velocity decreases from positive back to zero, and you get this beautiful looking trapezoid type thing. Now, let's talk about our car let's talk about making our graph go from velocity to acceleration, right? So now I'm going to apply the next graph rule. The slope of velocity is acceleration. This is a constant positive slope here. So we've got a constant positive slope. I'm going to make a constant positive acceleration. So constant positive slope on velocity, constant positive acceleration. All right, this is a zero slope right here. This segment right here is zero slope on velocity, so zero acceleration. And then for the last bit, we have a negative slope. And so then we have a negative acceleration. Now, let me just warn you, if you're watching this live, I know that I'm flipping through these pretty quickly. The expectation, honestly, is that if you need to, you're going to go look at the replay, okay? The replay posts 15 minutes after it's live. Now, if you're watching the replay right now, you feel like I'm going too fast, there's a pause button, there's a rewind button. Make use of those. This is good strategy for any of these videos that you're watching across any subject area. Okay, so here's an animation of what the car is doing. We can see the car speeding up, and then the car is going to have a constant speed, and then the car is going to slow down. Look at that. And so what we see that as the car speeds up, the velocity vector becomes more and more and more forward. The acceleration is in the same direction as velocity when you're speeding up, but if you're slowing down, the acceleration is directed opposite velocity. So we see the acceleration and the velocity are in the same direction, so the velocity is speeding up. No acceleration, velocity can't change. Acceleration is opposite velocity, you're slowing down. Okay, isn't that beautiful? So I just want to make you see that the velocity vector increases as the car speeds up, decreases, car slows down. The velocity graph's height, its value. So the value of the graph is how high up you are, zero value, positive value, same positive value, zero value. The value increases, stays constant, and then decreases. The position slope gets more steep, constant steepness, then becomes zero slope on the position graph. The car never moved backwards. But wait, it had a negative acceleration. But negative and positive acceleration don't tell you anything about how the car is moving. If you say acceleration in terms of direction it's moving, if you say negative acceleration, that could mean that you're going backwards faster, faster, faster. But a negative acceleration could also mean going forward slower, slower, slower. So just walking up to me and say, hey, Frensley, my car has a negative acceleration. That means, okay, are you in reverse and flooring the gas pedal? Or are you going forward and flooring the brake pedal, right? Okay, so acceleration direction doesn't tell me which way an object's moving. So acceleration is the same direction of velocity as the car speeds up, opposite velocity when the car slows down. Okay, so here's some guided practice for you. Here's a new story. Now we're going to need to make the cop happy. So when I was on the way over here, I totally planned on running a stop sign in my neighborhood until I saw the police officer was there. So what it is, I stopped and I just kept going, right? So let's say the car is moving with a constant positive speed. He's moving forward for the first 5 seconds. He thinks he can run the stop sign, but then he happens to notice the police officer, right? So for 5 to 10 seconds, he's going to uniformly slow down. He's going to stop only at the instant time equals 10. Only at time equals 10 is he stopped. So only for that instant. And then from 10 to 15, he's going to speed back up uniformly to the speed he was at before. So again, you're going to sketch these graphs. I personally might start with velocity and then go on to position or acceleration, but it's up to you. And I'm going to give you 3 minutes for it. Let's say 1 minute for each graph. So on your mark, get set, go. So as you're finishing up, I'm just going to tell you. So I have my own phone right here that's on the live stream just to make sure that it still works. And I have to touch the phone periodically in order to make sure it doesn't like time out or whatever and go to sleep. And so I touched the phone, and then for touching the phone on YouTube, it popped up with a little thing that said, if you like this video, you should watch this one. And it's like The Office Best Moments of Creed. And I'm like, what on earth makes you think that I'm the same as that, right? So there you go. That was kind of funny, I thought. Okay, so what do we got going on here? We've got a velocity graph, and if you'll look, we have the guy. He's going to go with constant velocity, and a constant velocity, just a flat line on his velocity graph. Then he looks over and he's like, oh my gosh, there's a police officer there, and I would not like to get a ticket today, right? And the police officer probably like, I don't want to deal with anybody today or for the next month. So this guy is like, let me just look like I meant to stop. So I'm going to slow down. And in the state of Texas, legit, okay, you can just be stopped for like an instant of time. No, this is a lie. You need to be stopped for 2 seconds, okay? But I didn't want to make you draw that. So he's going to stop for just a little tiny amount of time. The police officer says, okay, I don't have to pull you over. So he's going to speed back up, back to his normal speed, right? So let's change this velocity graph into a position graph, okay? So how would I change this velocity graph into a position graph? Here's what I'm thinking. I'm thinking that velocity is the slope of a position graph. This velocity is constant and positive, so I need a constant positive slope. How do I make a constant positive slope on the position graph? Constant positive velocity, constant positive slope. That's just going to be a straight line positive slope. So constant positive velocity, constant positive slope. Now we need our velocity to decrease to 0. That means the slope of the position graph has to smoothly decrease to 0. So here comes my slope smoothly, with no little parts that you're going to poke your eye out on, smoothly decreases to 0 slope. That signals the slowing down. And then now what I'm going to do is I'm going to immediately go back to speeding up. So how do you speed up? Well, I start with 0 velocity. So my segment here is going to continue having 0 slope for just a little bit of time. Then it's going to increase the velocity. So I need to have a slope that's increasingly positive. It's going to look like that one right there. All good. So as the velocity graph gets higher, the position graph is going to get steeper. And if the velocity graph gets lower into the negative, then the position graph is going to get more steep into the negatives, right? Changing velocity to acceleration, I don't think is that difficult. All you got to say is, hey, what's the slope? Positive, negative, or 0. This is a 0 slope, so I'm going to graph a 0 acceleration. And then we have a negative slope, so we're going to graph a negative acceleration. And then we have a positive slope, so I'm going to graph a positive acceleration. Oh my gosh, who would have thunk it, right? Okay, so hopefully not so bad. Here's again what it's going to look like. He's going to move forward with a constant speed. Oh no, there's a police officer. Let me just come to a quick stop. Okay, good. Now I'm just going to keep going. Good for me. All right. So what I want you to notice, that the velocity vector increases at the end when the car is speeding up, and the velocity vector decreases in this middle segment as the car slows down. The velocity graph's value increases for this last segment and decreases for the middle segment as the car slows down. The velocity graph goes down to 0. As the car speeds up, the velocity graph increases in its value. Remember, value is how high up on the graph you are, right? The position graph slope is going to increase at the same time the velocity's value increases. The position graph slope decreases at the same time the velocity's value decreases. The car never ever moved backwards because we never had a negative velocity. We did have a 0 velocity for a moment, but we never had negative velocity. And once again, acceleration is opposite velocity during the slowing down part. That's right now. And then the acceleration is in the same direction as velocity while the car is speeding up. That's that last little segment right there. Okay, cute. All right, all good. Oh my gosh, what on earth is this? This is every possible graph shape you might come across, as long as you stay within the realm of constant accelerations or constant velocities. So what's going on here? This up here is 7 different position graph pieces, then 7 velocity graph pieces, then 7 acceleration graph pieces, where each one of the same color shows the same motion. So what do you mean when you say that? Well, gray, that's standing still. So positions flat line, velocity 0, acceleration 0, standing still. This red, that's a constant forward velocity. So constant positive velocity is a constant positive slope. Positive velocity is constant, no acceleration. Here's your moving moving backwards with constant speed. So that box is not correct. That orange box needs to be edited. Sorry, I'm not perfect. I'm throwing these together at the last minute, like all your teachers are throwing together their stuff at the last minute. So this is a constant backwards velocity. So negative velocity, zero acceleration. Here is moving forward and speeding up. Here is moving forward but slowing down. Notice forward and slowing down is a negative acceleration. Moving backwards and speeding up is also a negative acceleration. And moving backwards and slowing down, that's a positive acceleration now. So should you memorize these? I'd rather you not. I'd rather you understand what's going on. But if you need to go to the replay and go back and pause and kind of study what's going on this picture here, then that's fine. But you may not get it all this first time around, and that's okay. It's okay to go back and watch the videos again and pause and rewind and that kind of thing. Don't play them on double speed. Play them on half speed. Okay. These two, or these three actually, these are the no accelerations. No acceleration, your velocity is a constant line, and your position graph is some kind of a straight line. Okay, all good. Here we have the two moving forward motions. If you're moving forward, then your position graph has an upward slope. Your velocity graph is in the positive quadrant, the first quadrant, right? But watch out, you can be moving forward and have a positive acceleration. You could be moving positive forward and have a negative acceleration. So just walking up to me and saying, hey, my car has a negative acceleration is not enough to tell me which direction you're going. Are you speeding up backwards or are you slowing down forwards if you have a negative acceleration? Okay, here are the two backwards motions. So you see the negative slope on the position graph. You can see the negative velocity on the velocity graph. It's down in quadrant 4, which is the negative quadrant, right? Once again, are you speeding up backwards? Then you have a negative acceleration. Are you going backwards but slowing down? Then you have a positive acceleration. And remember, slowing down means that the velocity graph is going towards zero. In fact, I think I mentioned that here in a moment. The yellow and the blue are both of the speeding up motions. So you can either speed up going forwards. That means that the graph becomes more and more, the position graph becomes more and more positive slope, or you can have a position graph becomes more and more negative slope. That's speeding up backwards. The velocity graphs are trending away from zero. That's speeding up. But watch out, just the word speeding up does not tell me whether it's a positive or negative acceleration. So if you say, hey, my car's speeding up, what's the sign of acceleration? You haven't told me enough information yet. Here are the slowing down motions. Both slowing down position graphs, the graph has a slope that's decreasing to zero. The velocity graph is trending towards zero. And again, just saying the word slowing down is not enough for me to judge the sign of acceleration. I need to be told the direction of velocity and whether the velocity is speeding up or slowing down before I can say the direction of acceleration. Okay, couple of things that are worth knowing. If your position graph is any part of a smiley face, then that's a positive acceleration, okay? So smiley, I don't care which part, the left, the right, any part of a smile on a position graph, you got a positive acceleration. And your velocity graph better be sloping up somehow. But if your position graph is any part of a frowny face, then that's a negative acceleration. That means that your velocity graph should be trending down somehow, okay? So that's all good. If you need to rewatch that, and you probably do, then don't feel bad. Everyone needs to rewatch it, including me. Okay, so now we're going to do some quantitative graphs here. We're going to do some quantitative graphs. So on this first one, I didn't mean to start the timer early. What you'll see here is you see the velocity and it's 8. You may need to press your face right up against the screen in order to see those little tiny numbers. Full screen everything, right? You got an 8 meters per second velocity until 2 seconds, and then it slows down to, and then reverses direction, got -8 at 6 seconds, -8 meters per second at 6 seconds, then slowing down to 0 at 10 seconds. So your goal is to make an acceleration graph with the right numbers, okay, so this is a draw, not a sketch, this is a draw, and to make a position graph. I'm going to tell you right now, I'm going to give you 3 minutes. One of those minutes is for acceleration, because I think acceleration is easy, but the other 2 minutes is for position, because position, going from velocity to position, is really tricky. Okay, so here you go. This is your time. On your mark, get set, 3 minutes, go. All righty then. Let's go from velocity to acceleration first, because I think that that's easy. So what am I going to remember? The slope of a velocity graph is acceleration. So I'm going to take this in just three pieces because it looks like three different slopes. First part, we've got a zero slope here for 2 seconds. So I'm going to draw a zero acceleration for 2 seconds. Okay, all good. Hope we're happy with that. Next segment, let's figure out the slope of this second segment. It looks like it goes down 8 and over 2, down 8 and over 2. So down 8 and over 2, that's a -4. So I'm going to graph on my acceleration graph a negative constant -4 between 2 and 6 seconds. Okay, so there you go. Now, here's another programming note, okay? Now, if you're watching at home and you're like, hey, this guy's drawing like vertical lines in between his segments on an acceleration graph. Should I do that? Well, strictly speaking, no, you shouldn't, okay? That will make your math teacher have a hemorrhage, all right? That makes it not a function, and so what you're supposed to do is you're supposed to do the little open and closed circle thing. Physicists don't care that much, okay? I draw the vertical lines because they make me feel good inside, okay? So if on an AP exam you draw the vertical line in, we're not going to ding you for it. But if you do that on like your calculus exam, or if you do it in your math class, then your person might bite your head off, and we don't want that, okay? We need to make the math people happy, all right? But on AP Physics, we don't care if you draw that little vertical line right there. I draw it because it gives me a warm, fuzzy feeling inside, okay? Now, what is the slope of this thing right here? Looks like we're going up 8 and over 4, so I think that's +2. So my graph is going to jump up to +2. It's going to go over +2, and I make the vertical line because you know what? That's how I feel about math people. No, I'm joking. Okay, please don't send a square root at me. Okay, now how am I going to go from velocity to position? This is the part that's really tricky, okay? So I know you know the rule. You're like, hey, the area of a velocity versus time graph is position, right? And I'm like, no, the area of a velocity versus time graph is how much your position changes. It's how much your position changes. Now, I think it said on the slide where the timer was timing down, I think it said that to start position at 0. Just so you know, if you ever go from acceleration back up to velocity, you have to be told where to start. If you go from velocity back up to position, you have to know where to start. For those of you in physics C, you know that's because that when you take an integral, there's that plus C. The only way that you can deal with the plus C is to have some kind of information about where you start, right? For those of you who are in physics 1, you're going to pretend like I didn't just say that. Okay. So what have I done here? I've split my velocity graph into 4 shapes, and I've color-coded them for your convenience. Remember, the area is always bounded by the graph, the horizontal axis, and 2 vertical lines at the start and end of that particular motion. So I start with this red graph right here, or this red piece, and I'm going to call them panels from now on. So I have the red panel, the green panel, the blue panel, and the purple panel. If you're colorblind, sorry. Okay, so red panels right here. So that's 2 by 8, so that's 16. Well, that doesn't automatically mean that you're at 16. It means that you've moved forward 16. So since I'm from Texas, everybody in Texas worships football, okay? So I have to talk in terms of football and cars to everybody. So here's what I think. I'm like, hey, I want you to imagine football, only this football is in meters like it should be, okay? And so let's say you just did not a 16-yard play, but a 16-meter play. That doesn't mean the ball is on the 16-meter line. It means it moved ahead 16 meters. So if I was at 0 meters and I advanced forward 16 meters, that's what this area represents, then now I'm at 16. Notice, I drew a dot. I'm not connecting the dots yet. I'll do that later. Please take the area of this green panel. It's also 8 tall and 2 wide, but it's a triangle, so it's half. So it's not 16, it's 8. The green panel's area is 8. That does not mean that the object is at a position called 8. It means it advanced forward 8 more meters. If it was at 16, and the area of the green is 8, then that means that the object is now 8 meters ahead of that, also known as 24. So now the object is at 24. Well, much like the Cowboys, I'm going to get so much hate mail, but I live in Dallas. For every good play, there's got to be an equal bad play, right? So here we go. We're going to lose our 8 meters. That's an area that's below the axis. So if the area is below the axis, then that means that you are losing, you're going backwards, you're losing a meterage rather than yardage, right? So this blue panel has an area of 8. So we're going to go from 24, we're going to step backwards 8 meters. So we're back at 16. And then this purple panel has an area of -16, negative because below. So we're going to lose our 16 meters that we start. So we're going to be all the way back at 0. And that's just the way it goes, right? Yep, that's just about every season. So there you go. Now, I need to connect it with the graph shapes, right? So do I connect it with the line or with the smiley or with the frowny? I'm not encouraging you to memorize each of these that was on that page with the 7 different columns, right? But just understand. So here's what I'm thinking right now. So rather than memorizing, I want to understand. The velocity is constant for the red first interval. Constant velocity. Velocity is the slope of a position graph. So if the velocity is constant, the slope is constant, and a constant slope is a straight line. A constant slope is a straight line. Now, the velocity is, for the green part, the velocity is positive, but decreasing to 0. The velocity is positive, but decreasing to 0. So for the position, I need a slope that is a positive slope and then decreases to 0 slope. How do I make a slope that's positive and then decreases to 0? I'm going to have it down like a frown. Yep, it's going to be down like a frown. Yeah, my students know I call it that. So parabola that's like this is a down frown, right? So I've got my velocity graph is decreasing to 0 from positive 0. The slope of position is positive, then smoothly transitions to 0 slope. For the blue segment, we now have 0 velocity transitioning to negative velocity, 0 velocity, then negative velocity. So we're going to have 0 slope, then negative slope. Notice the position graph has no points where you can poke out your eyes. For those of you in calculus, it is differentiable everywhere, right? It's a smooth curve everywhere. It's differentiable everywhere. Last purple piece. And you'll notice this is the same color coding I used on that slide way back with the 7 columns. So what was purple on that one? That was moving backwards and slowing down. So here we have a negative velocity slowing down to a 0 velocity, a negative velocity slowing down to a 0 velocity. So I'm going to have a negative slope, and it's going to become less and less and less steep till I end with a 0 slope. Look at that. So to make the position graph, it's a 2-stage process. Stage 1, get the points down on the page using the areas of each panel. Then connect with the right graph shapes. That's the two steps. Okay, here's another example. We're going to check for your understanding. This one's going to be a little tricky. We're going to start with velocity equals 0, and we're going to start with position equals 0, both at time 0. So, but look, I gave you an acceleration versus time graph. No acceleration, positive 3 acceleration for 2 seconds, no acceleration, negative 3 acceleration for 2 seconds, 0 acceleration. What are the other 2 graphs going to look like? You got 3 minutes on your mark, get set, go. This is our last practice of the day. 4 minutes, because it's going to be a little bit more tricky. All right, folks, here we go. So there's a couple of ways you can go about this. One way is to just look at the acceleration graph and go panel by panel and ask yourself, what's the area? The area of the first panel is 0 because the graph is right on the axis. This area is 6, area of 0, area of -6, area of 0. So here's what I'm thinking. Area of 0, the velocity does not change. So the velocity was 0, it doesn't change, it stays 0. Now, this area is 6. That means that we gain 6 velocity. So we go from 0, gain 6, now we have 6 velocity. The other way you can do it is to just say, hey, the acceleration is 3. So let me just draw a line segment whose slope is 3, because the slope of velocity is acceleration. 0 area for the middle segment, that means the velocity does not change. The velocity doesn't drop back to 0. The velocity just doesn't change. 0 slope, or excuse me, 0 acceleration, 0 slope. 0 acceleration, 0 slope on a velocity graph. Lose 6 meters per second. That's what this green area means. -6 meters per second of area, lose 6 meters per second. Lose all 6. Then you end with no acceleration, so the velocity still can't change. So you could have done it by areas, or you could have just said, hey, 0 slope, slope of 3, 0 slope, slope of -3, 0 slope, which is what the accelerations are. Now I'm going to split that trapezoid into areas. Okay, so the first area is 0, so no change in the position. This area I think is 2 by 6, but it's a triangle, so that's 6. 6 area for the yellow, so I advance forward 6 meters. The red area is 12. So from 6, I advance forward. So it's a 12-meter play. So if the ball was on the 6-meter line and you just did a 12-meter play, then now the ball is on the 18-meter line. So the area panels tell you how far ahead you've gone in that interval. Not where you are, but how much ground you've gained, right? This last panel is also an area of 6. So we advance forward 6 meters again, finally reaching 24. And that's where we're going to end up, because the last little bit is 0 velocity. 0 velocity means we cannot change our position in any way. And then let's put it together with the shapes. If you have a constant velocity, then you have a straight line for your position graph. If you have an increasing velocity, then your slope is increasing on position. If your velocity is decreasing to 0, then your slope is decreasing to 0 on position. Okay, so where can you go to practice this? Let me just show you the summary. It's just the same rules that we did already. Okay, slope of position is velocity. Area of velocity versus time is how much position changes. The slope of velocity versus time is your acceleration. The area of acceleration versus time is change of velocity. Those are important rules to know. It's all good. If you're in calculus, of course, you should be thinking the derivative of position is velocity. The integral of velocity with respect to time is position, right? Say it in calculus words. I'm going to put this slide back up in a moment. There's an old AP exam that is now defunct called AP Physics B, where there's some good practice for this on their free responses. So what I'm going to do is I'm going to share a different screen now with your permission. And the screen I'm going to share looks like this. So if you'll have a look, this is my browser window right here. I look up AP Physics B exam, and the first link should be this old AP Physics B exam that tells you that it's been replaced by Physics 1 and Physics 2. But if you look down, you'll see that there's a bunch of free response questions from the past. So the last examination was in 2014. So there's 2014 all the way back to 2000 or to 1999. Please note that some of them are called Form B. Okay. So what I've done on this other slide here, if you will have a look, let me see if I can share that. So this is a list of questions that will help you with this particular topic. Please note that every free response set also comes with something called scoring guidelines. So that's where you can find the solutions to each one, right? So I'm about to flip over onto the final slide. So if you need to, you can watch the replay and you can just come back, pause this screen and take a picture of it with your phone or something like that, right? Okay, well, that's going to be it for today. Tomorrow we're going to do some more one-dimensional motions. Half it'll be something that's P1 compatible. The rest is going to be calculus-based stuff. So that's going to be Physics C. Look for me on Facebook, and I don't know. My phone still wants me to watch the best of Creed. I mean, is that what's relayed to me? I don't think I'm Creed from The Office. So here's what you can do. What you can do is you can message me on Facebook and just tell me which character from The Office do you think I'm like, okay? All you got to do is not say Creed. Don't say Creed. And don't say Michael either. Don't say Dwight, okay? Don't say Jim either, or Pam. Don't say Stanley or Phyllis. And not Ryan. Don't say Kelly Kapoor either, and don't say Toby. Definitely don't say Toby, and don't say Kevin. Don't say Oscar. Don't say Angela. Don't say Jan either, or David Wallace. Don't say Daryl from the Warehouse either, or Patch or the Sea Monster. Yeah, pretty much anybody else would be good. Right, to talk about. Don't say Andy. Okay. I don't like Andy, but you can say anybody else from The Office that you think I'm like, okay? So I'll see you tomorrow.